Okay.
Okay, go for it.
Just 1 second. Yeah, hi everyone. My name is Haolun, and I'm now a PhD student at McGill University in Mila. Basically, my research interest focus on information retrieval, fairness, recommender system, and also continual learning, something like that. And today's my honor here to present my work. And actually, this is a work co-author with Pascal, and he's also here today. The title is Joint Multisided Exposure Fairness for Search and Recommendation. This work has already been presented in SIG-IR and also the symposium AI Montreal. So firstly, for some quick background, we know in order to reduce the information overload, the recommender system and the information retrieval system have emerged, and they have been a very important role in modern society. So basically, this kind of systems, they rank the items, follow the probability ranking principle, which is to rank items in decreasing probability of relevance so that they can maximize the utility of the whole ranking list. And from another perspective, we can understand this kind of system as actually they can decide what kind of information can get exposure. So for instance, on the right-hand side, as you can see, if there are 6 items and the blue bar shows the relevance score of their of each of them, actually you can see the exposure may be something like in the yellow bar. So there will be a very big difference compared to the blue bars. This is because like humans mainly focus more on those items ranked at the top of the list. So as you can see, there will be some unfairness problem here. So for instance, if you compare, let's say item 1 with item 4, as you can see, the relevance does not have very big difference. But actually the exposure is like they are about 2 or 3 more times compared like item 1 of item 4. So actually there are some exposure unfairness problem here. So actually the exposure unfairness has already been observed in many fields, and many researchers have also found out there are many harms for this exposure unfairness. So for instance, one of the examples is the representational harms. So for instance, if you search a SEO query in a search engine, maybe the result will be returned like this. So as you can see, it cannot show a real proportion of different genders or races in the real world system. As you can see, like this result lists maybe are all white males. So there are no females or other researchers or other CEOs here. So actually this is a kind of bias. So this is the representational harms. And also in addition to the representational harms, there are also some other harms like allocative harms. So for instance, some media and some researchers also find out that online ads for high-paid jobs are targeting men more than women, and also even other non-binary people. And actually this kind of problem, like one professor from SMU, he also did such kind of research experiment. Like they randomly constructed several profiles for female users and male users, and finally they found out that the male users were showing the high-paying ads about 1,800 times compared to female users who saw this as about 300 times. So there's a big unfairness and bias here. So actually this second example exactly motivates our research here. We want to think about like why this problem is hard to solve. And also like, do there exist any metrics we can measure such kind of unfairness? So we take a step back and look at like what are the prior definitions of fairness in the field of information retrieval and recommendation systems. And we found out that basically there are 3 lines of definitions. So the first one is they define the fairness on the item side. Basically, they want to ensure the equality of exposure for individual of items or group of items. So this is also the individual fairness and the group fairness. So this is on the item side. And the second one is on the user side. So basically, they want to ensure the equality of satisfaction for individual users or group of users. And actually, there are a third kind of one, which is the fairness for multi-stakeholder. Actually, we also have a paper on this just accepted by the Toys Journal. The idea is that we not only want to consider about just one single stakeholder, we consider about multiple stakeholders, but actually most of research on this line, they still separately model the fairness for each stakeholder and then use some scaling factors to combine them all together. And maybe you can use some multi-objective optimization problem method to finally achieve a parity optimal. But as you can see, they still separately model the fairness for the user side and the item side. So we think, like when we take a look at the prior definition of fairness, we found out that the limitation here is exactly what I just mentioned, is that they never jointly model fairness from the view of both sides. They treat them separately. But actually, we know that in the recommendation system or the information retrieval, actually the nature is the interaction between like the users and items, or the sometimes the users can be the queries. So our thinking is that when we talk about the fairness problem, we still want to achieve them in a joint way. We want to model the fairness jointly, consider multiple stakeholders. So this is a main motivation of this work. And our argument here is that if we want to consider about the exposure fairness, it should be a joint multisided problem. In other words, we should not only consider about whether content receives exposure, but also whom it is exposed to. So this is the key argument. So if we start from the prior definitions on exposure fairness, as you can see, we just mentioned there are about two definitions, the individual fairness and the group fairness. So if we take the job recommendation as example, the individual fairness means that you don't want any individual job be under or overexposed in the whole system. And the group fairness can be regarded as you don't want those high-paying jobs or low-paying jobs be under or overexposed in the whole system. So actually, as you can see, they did not consider about, say, user dimension on the user side. So actually, implicitly, they just consider about individual user. So in this case, we reframe these two terms as I fairness and IG fairness. So the first I here indicates the dimension of the user side, which is the individual. And the second letter here indicates the dimension of the item side, which is the I for individual and G for group. So in our work, we want to consider about the dimension on both the user side and item side. So very intuitively, we can extend these two metrics into two new metrics, which is called GI fairness and GG fairness. So here, the first letter G indicates that we now incorporate the group dimension, the group information on the user side. So here, like the GI fairness can be regarded as whether individual job are under overexposed to group of users. And also GG fairness here means that whether the whether the high-paying jobs and low-paying jobs are under overexposed to male users, female users, or non-binary users. So this is exactly the example we used before. And if we take one more step further, we feel like it also makes sense that we have a more stronger aggregation on the user side. So in this case, these are the two last new metrics, which is AI fairness and AG fairness. So the A here means all. So all the dimension, like all the users in the whole system. So here they like take the AG fairness as example. The AG fairness actually shows like with a group of items being under overexposed in the whole society to all the users. So like one example is whether those companies owned by Black people are underexposed in the whole society. So this is the motivation and how they connect to the real world problems. Yeah, and basically now we call these 6 fairness metrics, including the 2 existing ones, the IF fairness, IG fairness, as a joint multi-site exposure fairness metrics, because they jointly model the exposure problem from both sides, both the users and items. Yeah, and this is just an example, and I guess I have really demonstrated like what each metrics means. Yeah, so to make you understand this idea more clearly, we give a 2 example here. So for instance, we assume like there are 4 jobs here, and also there are 4 users here, and 2 of them are high-paying jobs, 2 of them are low-paying jobs, and 2 of the users are men, 2 of the users are women. And for each user, we assume that each user, let's say he or she has the sum of exposure as 1, and he or she will equally distribute the exposure to all the relevant and observed items. So if we assume that all these 4 jobs are relevant to all the 4 users, then the target exposure, which is the ideal allocation, should be a uniform everywhere, because every job is relevant to every person. So this is the most fair situation to allocate the exposure of these items. But actually, this is just the ideal allocation. So what if we consider about if I have 3 recommended systems? Like for instance, as you can see, here are 3 recommended systems, and for each recommended system, it recommends 2 items to each individual user, and they have different recommendations. So basically, you can understand this as 3 different recommendations. So for each recommendation, we can have we can compute the exposure like derived by this recommended system. So we call this a system exposure. So here are 3 system exposures. So at the first glance, you may feel like it's very similar, but if you exactly compute the metrics we proposed, you will find a difference. So for instance, if you first compute the II fairness and IG fairness, which is the traditional individual fairness and group fairness. So here I only show the result of the group fairness. You will find out like the result is the same for all these 3 systems. So this is very intuitively because, like as you can see, in each system, there are 2 relevant items from a same group not being recommended to each individual. So in this case, like the group of items are the same level of underexposed or overexposed to other users across the 3 systems. But actually, it's not the same, right? I mean, these 3 systems, actually, you can feel like there's a difference, but as you can see, maybe the relevant is the same, and maybe the IG fairness, II fairness is the same. So the difference is if you compute with the other dimension of the fairness matrix, you will find the difference. So for instance, if you check the GG fairness, so the GG fairness here means that whether the group of items are under or overexposed to a group of users, you will find out that like in the first system, the GG fairness is 0. So basically the 0 here means that it's fair. This is because like in the first system, those high-paying jobs go to 1 man and 1 woman. Those low-paying jobs also go to 1 man and 1 woman. So in this dimension, we can regard it as fair. But actually in the second system or the third system, so for example, for the second system, as you can see, those high-paying jobs only go to the men and those low-paying jobs only go to the women. So this is unfair situation. So if you compute this, you can find out like the second and third system, the GG fair is larger than 0, which means the second and third system, they are not GG fair. And also, if you look at the last dimension we proposed, so here we also still use the AG fairness as an example. So basically, the AG fairness means that we want to capture whether a group of items are under or overexposed in the whole system. So as you can see in the first system and the second system, the AG fair is 0, which means they are AG fair. But actually in the last system, because as you can see, the low paying jobs are never being exposed. So it is not AG fair. So the AGF, when we compute this value, it will be a value larger than 0. So here I just omit how we exactly compute these values, but the key idea here, as you can see, is if you use traditional pure relevance matrix or the individual fairness or the group fairness matrix, you may not capture the slight difference between different systems. But introducing our proposed matrix, you can see like how these systems exactly they are different and at what dimension they are different. Yeah, so basically this is the key idea of this 2 example. And next is to how to formally define the GMA fairness matrix. So basically here we follow actually still Fernando and Basquez's paper and before. So the key idea is that we want to measure the disparity as a difference between a system exposure and target exposure. So this is exactly the 2 example shows, like there is a system exposure matrix and the target exposure matrix. So basically for the system exposure, it is computed based on our current like ranking policy. So basically, it will maintain a user item into okay. It will maintain a matrix which is E here. The E, it's the user. The size of E is the number of users by the number of items, and basically in each entry of this E contains the exposure given a specific user and a specific item. So the U here is user, the D here is item, the epsilon here means exposure. So basically we will use some user browsing model and the stochastic ranking policy here to compute it. So for the user browsing model, basically the user browsing models are some simplified models of how users expect and interact with retrieved results. So basically here we use a RBP user browsing model. So the idea is very simple. The idea is that we assume that the user's patience for browsing a list will decrease exponentially. So for instance, on the first position, maybe her patience has 0.9, but on the second position, maybe her patience will be 0.9 squared. And on the third position, it will be multiplied by 0.9 again. Yeah, so basically this can show that the users will focus more on those items ranked at the top of the list. And basically here, the stochastic ranking policy, I will talk about that later, but the key idea here is that in most cases, in most systems, they only consider about the deterministic ranking, which means like, for instance, if I have 6 items, let's say if their score is 100, 99, 98, and 80, 70, 60, you will just consider one ranking list, where the 100 will rank at the top of the list, and the 99 will rank the second of the list. However, as you can see, in our first motivation, as I guess we also mentioned, like the relevance score, they do not change too much. They don't have very much difference. But actually, if you rank like this, let's say the 100 item and the 98 score item, their exposure will be a very big difference because of the users only focus more on those top ranked items. So the idea of the stochastic ranking policy is that we don't consider only about one single ranking. We consider the distribution of we consider the probability of a distribution of rankings. Like for each ordering, there will be a probability we can consider. So for instance, like if you rank like 199, 98, there will be a probability. This probability maybe will be very high, but also there will also be some probability like you ranked 99 above 100. So there's still some probability we want to consider about this. So this is the key idea. I guess I will talk about that later, but basically by doing this, as we can see, we can more fairly allocate exposure among different items. We will not only follow one static ranking policy. Yeah, basically this is how we compute the system exposure. And for the type exposure, basically is we should assume some ideal the exposure allocation matrix. So for instance, in our toy example, it's just uniform everywhere, but actually you can use other different policies. Like, basically mathematically, it can be written like this. And here you can still use some RVP model to assume the user browsing model and then compute this. But I think in our implementation, basically, when we compute the tag exposure, we mainly still based on the like the true relevance label in the user item interaction history. So that is how we that is also how we incorporate the relevance into the tag exposure computation. Yeah, so basically it's the key idea. And also one note here is that if we replace the user with query, so as you can see, the recommender situation will become an information retrieval situation. So this is how this framework can be applicable in both the recommendation scenario and also the information retrieval scenario. And after we have the exposure and the system exposure and tag exposure, how we compute the difference, how we exactly compute the each metric is just a difference between these two terms. So for instance, for the IF, the individual fairness, and the GGF group fairness, as you can see, basically the blue, the term underlined by blue is the system exposure, and the term underlined by red is the tag exposure. And the only difference here is that you will have different aggregation on the user side or the item side. So this is the only difference. And also like if you write everything out, it will be something like this. So there are 4 metrics, and you can see in there are 6 metrics, and in each matrix, there will be a GIJ minus GIJ star, which is the difference between the system exposure and tag exposure. And the other part is just the aggregation, the user side and item side. Yeah, so this is the formal definition. And after the formal definition, we do some analysis. So the first analysis is the intra-metric analysis, which is that for each metric, we want to know like what components it has inside this metric. So the main observation here is that we found out like each metric can be decomposed into 3 components. So one component can be regarded as a disparity, and one component is the relevance, and one component is the components. Oh, so sorry, it's a constant. So basically the disparity here is easy to understand. So let's assume that, for instance, if we have a vector, the sum of this vector is a constant. So how can you make the sum of the square of each entry be the lowest? So for sure, the method is to use a flat distribution to make every position have the same value, to make them very fairly distribute the whole sum. So that is why like the first term, the EIJ square, it can be regarded as a disparity. So basically, the more fair situation, like if I make the value in the EIJ in the E vector, like everywhere is the same, the disparity it will be the smallest. So this is why the EIJ can regard the first term, the EIJ square, can be used to indicate the disparity. And also like in the second term, like we just mentioned, like how exactly compute the GIJ star, because it is exactly based on the relevance. So the second term can be regarded as a relevance component. And the third term, because it's just a constant if your user item interaction history is fixed. So the GIJ star is computed based on that user item true relevance label. So the third term can be regarded as a constant. So in the exact computation, maybe we can just ignore this term. So the reason why this decomposition is great is because if we can minimize this matrix, it can be regarded as minimize the disparity component and maximize the relevance component. So this is exactly what we want, because we want to minimize the disparity and at the same time maximize the relevance, because there's a trade-off here. So by doing this, you can also see that our proposed matrix exactly has a trade-off between the disparity and relevance. So we are not like other metrics which only consider about the fairness or only consider about the relevance. So we jointly model these two things together in a single metric. So this is the benefit of this kind of decomposition. Yeah, and also this is just an example for the IAF, and you can also write the other parts for the disparity components and relevance components for the other metrics. So the idea is similar. And like further, we use this example to kind of like to verify like how the stochastic influence the different components of the matrix. So basically here we use a Plackett-Lucey model to construct a ranking by actively sampling items without replacement to achieve the stochastic ranking policy. So basically the beta here controls the stochastic, and the YDU here is the relevance score between a user and the item computed using other recommendation model, for instance, like metric factorization, or you can use other more advanced model like graph neural network. That also makes sense. So basically here, as you can see, on the left-hand side, when the beta is large, which means there's a high stochasticity. So when the stochasticity is high, the disparity will be low. Because if you randomly recommend anything, the disparity should be low. But also, as you can see, the relevance will also be low because you are randomly recommending something. And also, like on the other hand, if the beta is small, the disparity will be high, and also the relevance will also be high. So this can also show, like, to verify there is exactly a trade-off between the disparity components and relevance components in different metrics. And actually, we also studied like how different models have the different trade-off on the fairness components and disparity components. So I guess we studied like the BPRMF, LDA, pure SVD, like many models here. And this image show the x-axis shows the disparity components on 6 different Jimmy fairness metrics, and the y-axis is the corresponding relevance components. But I think the one limitation here is that actually in our previous work, we didn't very carefully study like why this will happen, like why which model can have a better trade-off and why which model can have a worse trade-off. So I think maybe this will be a future work. I will continue this line of research. Yeah, but like in the previous version, we didn't very systematically study the reason behind it. Yeah, so that is for the intra-metric analysis. So we also study an inter-metric analysis. So the inter-metric analysis shows that for different dimensions of the fairness of the Jimmy fairness matrix, one is the correlation between them. So basically here we use the Multisided data set. So there are 2 sides. So one side is user and one side is the item. So there are some attributes on them. So basically here we compute the Kendall index between like different dimension of the Jimmy fairness matrix. So the first table shows the disparity components of these 6 different metrics, and the second table, the second figure shows the relevance components of this 6 different Jimmy fairness matrix. So basically here, as you can see, in the 4, newly proposed dimensions, they have a very strong correlation compared to the other two existing one, which is the individual fairness and the group fairness, the IAF and the IGF. So this can potentially indicate that our newly proposed four metrics are significantly different from the two existing one. So in this case, maybe our new metrics can also capture something that if you only use the existing individual fairness and group fairness may not capture. Yeah, so this is the main idea of this. And for the last part is that we are concerned about, like, since we have this new metrics, can we directly optimize the ranking models for the target exposure? Like because in our previous intra-metric analysis, we just mentioned, like, if we can directly minimize the IF fairness, it can be regarded as minimize disparity and maximize relevance. But how can we directly optimize that? So actually, there are two challenges here, and both challenges occur in how we compute the system exposure. Because basically the target exposure, once the user item interaction matrix is given, you will just simply compute it and you will treat it as targets there. But actually the problem is the system exposure, because in the system exposure, there are two parts has a challenge. So one part is we are using a stochastic ranking policy. So what we're exactly doing is we are using a packet-Lucid model to sample the multiple rankings to obtain the stochastic ranking policy. So actually this kind of sampling operation actually is not differentiable. So the solution here is that we add some gumball noise in the score, the YJ. So basically the YJ here is still like the computed relevant score between item and the user. We independently sample some gumball noise in to add them in this original ranking score, and we just we can just sort the this approximate probability on the right hand side in the first table. We just sort them. After we sort them, we can get the approximate the ranking position of the items. So this is one solution for this one. So we don't need to do the sampling from a discrete distribution like iteratively. But actually, this sampling of the p tilde have a second challenge here, is that the ranking is also not differentiable as well. So we need this ranking position because we are using the RBP user browsing model. So the RBP user browsing model, as we discussed, the user's patience will decrease exponentially based on the ranking position. So basically, we need that ranking position of items to be differentiable, but actually the ranking is not differentiable. So the solution here is to employ a smooth rank. So the smooth rank here is that we pairwisely compare the probability p tilde between two items in a ranking list so that we can approximate the rank position of each item. So this is the key idea. So after we're doing this, we can have a differentiable ranking score, which is smooth rank here. So then we can compute the system exposure and optimize them in a differentiable way. And this figure is from Baska. This can very perfectly show like what is the gradient-based optimization for the target exposure framework looks like. So basically, firstly, you have some items, and you will use some model to compute the scoring, like the score of each item, and then you will have this like there are four bars here. The blue one, the green one are longer, and the other one is shorter. So basically, this means that maybe the blue one, the green one, they have a more higher score compared to the other two. And then we need to do some stochastic ranking policy here. But our solution is to add independently sampled gumball noise in them. And after that, we use the smooth rank idea to compute the smooth rank value so that we can get the approximate rank position. And then we compute exposure using the user browsing model, like the RBP. And then basically you will do this sampling for multiple times. So for instance, here just show example, like you only sample 4 times of the gumball noise. But actually in the real world system, I guess we sampled about, more than 200 times of the gumball noise to better approximate the real rank position. So after that, in this calculator, you just compute the average exposure, like based on your multiple samplings. So in the end, you will get the system exposure. and you compare your system exposure with the target exposure to compute the difference based on the Unfairness matrix. And then you use that objective to do the optimization. Yeah, so basically this is the overall pipeline. Yeah, and for the optimization, so here we just do one single example. We use the IF fairness and the GG fairness to combine them all together to as our training objective. So the reason why we have to use IF fairness is that because if we only use GG fairness, we will not consider whether a group of items are overexposed to group of users. We will not achieve a high relevance of the recommender system. So we have to use IIF here to make sure that the recommender system will also have a high relevance value. So basically, the IF fairness here is very similar to the BPR ranking loss or the rank net loss. So it's used to make sure that you like for at the individual level, each user can get their their pleasant items. So this is to make sure that the system has a high relevance. So that is why we have to use IIF, and also we combine IGGF here. So basically the experiment here shows that we can significantly minimize the GGF with minimal degradation to the IIF and the relevance. So we still want to use the movements 100K and movements 1M as an example, because at that time we feel like we can't find a very good data set on exactly the job recommendation, because maybe there are not many many data sets have that kind of information, like which high paying jobs, low paying jobs go to which female or male. So maybe in the future we will try to extend this experiment on more different scenarios to verify this idea. Yeah, so for the summary is that in this work we propose a joint multi-site exposure fairness matrix that deal with the different types of systems biases in counting exposure from recommended systems. And also we decompose them into disparity relevance components and study their trade-offs. And also we propose a differentiable way to directly optimize this matrix. And for the discussion and future work, so here I listed 3 of them, which I think is important. So the first one is the group of attributes. So I guess in the last week's meeting, I'm also asked the speaker like how we can deal with the intersectional fairness. So because like each user may not only belong to one group. So in reality, maybe like one person may belong to multiple different demographic groups. So in that case, if we still want to use this framework to model the exposure, so how can we achieve it? This will be a challenge here. And also the second one is that in this work, and also I think in most works in unfairness in information travel recommender system, when we talk about the multi-stakeholder, we still mainly focus on 2 stakeholders, which is the consumers and the producers. But actually there are really maybe other stakeholders in addition to these 2, like the manufacturers or retailers or something like that. So if we want to model like more than 2 stakeholders in this exposure fairness metric, in this exposure fairness like the framework, how can we define exposure fairness? Like what is exactly the fairness going to achieve for different stakeholders? This also will be a challenge problem. And the last one is, yeah, this one is also proposed by Basca. Like when we use the stochastic ranking policy, like for now, what we're doing is that we just randomizing a static policy with the model independent sampling of the gumball noise. But actually, how we can also incorporate the model's own uncertainty during the sampling. So maybe this will be a more challenging question. And if we can solve this, this will not only be related to the fairness problem, maybe it can also be related to other like ranking or information travel problems. Yeah, I think that is all of this talk. And thanks everyone for being here. And also thanks Pascal for being here. Yeah. If you have any